Okay, now we review the inverse matrix. What is the inverse of a matrix? The definition is if A times B multiplied by B equals the identity matrix, then we say that B is the inverse of A. Also, A is an inverse of B. That's the definition of matrix. If if multiplication of two matrices is identity matrix, then they are inverse of each other. Of course, we require that A, B are square matrix. Of course, because the identity matrix is a square matrix. Okay, that's the definition. Then there's two problems. The first one is how to find the inverse matrix, and the second is when a matrix is invertible. The first problem can be used this theorem. And we can find use this theorem to find the inverse. If we multiply a matrix or invertible matrix multiply our inverted matrix on the left is equivalent as a series row reduction, series row operation, maybe row operation. As a series row operation on the matrix. That means A is equivalent to row operation of A, or row operation on A, row operations on A, if M invertible, if M is invertible. That means, and use this theorem, we can find the inverse of our matrix. That is, to find the matrix of A or to find A inverse, we do the row operation as A and I. This is a bigger matrix. That is the A is matrix as the first and I as the second matrix in combined as one bigger matrix. And we do the row operation for this matrix. And if the A is changed to the identity matrix, and then the identity matrix is A inverse. Maybe we call this is B. Then B is A, the inverse of A. Why? Because A I. If we multiplication this matrix by A the inverse of A, then the first matrix becomes identity and the second becomes the inverse of A. Because the multiply or an invertible matrix on the left is equivalent to a series of row operation. So this means that is this matrix can do row operation to here. Then the B is the inverse of A. If we want to find the inverse, we always use this trick. Now let's see example. A equals 2, 7, 1, 1, 4, negative 1, 1, 3, 0, and then find the inverse of A. So we use this trick, A and I, that is 2, 7, 1, 1, 0, 0, and 1, 4, negative 1, 0, 1, 0, and 1, 3, 1, 0, 0, 1. We use dashed lines to separate these two parts. We only need to consider of the first part and do the same row operation with this previous part of the second part. So we do the row operation. So the first we interchange the first row and the third row because the third row is the easiest row. The simplest, its simplest form. And then 1, 4, negative 1, 0, 1, 0, and 2, 7, 1, 1, 0, 0. And then the second row subtract the first row, and the first row times negative 2, then add to the third row. The second row subtract the first row, it's 1, negative 1, and then 0, 1, negative 1. And the first row multiplied by negative 2 and then add to the third row. So this is 1 because 3 times 2, negative 2. Okay, this does not change. It's not change. That's negative 2. And then the third row subtracted the second row. That is 0, 0, that's 2, that's 1, that's negative 1, negative 2 minus negative 1, that is negative 1. And then divide the third row by 2. These two rows these two rows are not changed. And 0, 0, 1, that's 1 half, negative 1 half, negative 1 half. And then the second row subtract the third row. So add the third row. 1, 0, 1 half. That's 1 half, That's 3 over 2, negative 3 over 2, 0, 0, 1, 1 half, negative 1 half, negative 1 half. And then the first row subtracted the second row multiplied by negative 3 and then add to the first row. So this is 0, that's 0, times negative 3. So that's negative 3 over 2, negative 3 over 2 times negative 3, and that's negative 9 over 2. Oh, that's 9 over 2. That's 11 over 2. That's 0, 1, 0, 1 half, 1 half, negative 3 over 2, 0, 0, 1, 1 half, negative 1 half, negative 1 half. So the left part is changed to the identity. So we got the inverse of A is negative 3 over 2, negative 3 over 2, 11 over 2. That's 1 half. That's 1 half. Negative 3 over 2, 1 half. Negative 1 half. Negative 1 half. That's the solution. Use the row operation or row reduction to reduce A to be identity, and then the identity is changed to the inverse of A. That's how to find the inverse matrix. The second problem is related to when a matrix is invertible. A is invertible, is equivalent to some conditions. That's equivalent to the first one. First one is Ax equals 0 has only trivial solution. The second one, by the computation before, we know that A can be reduced to the identity. The third one is Ax equals B has unique solution. The fourth condition, all those conditions are equivalent. The determinant of A does not equal 0. The fifth, that is the rank. Rank A is n, and we always use this one and this one. These two criteria are common used. So if we want to determine our matrix is invertible or not, we use the rank or the determinant. The rank one is the most efficient way to determine our matrix is invertible or not. Let's see an example to determine. determine if A equals maybe 1, -1, 2, -5, 7, -11, and -2, 3, -5. If it's invertible or not. The solution is we can use the rank. The matrix is 3 by 3, so we use the row reduction. A is 1, -1, 2, -5, 7, -11, -2, 3, -5. 1, -1, 2 times 5 add to the second row. That's 2. That's -1 times 2 add to the third one to the third row. That's 1 times times 2. That is -1. 1, -1, 2, 0. We multiply the third row by -2 and then add to the second row. So this is 0 times -2. That is 2 minus 1. That's 1. 0, 1, -1. Interchange the third and the second row. That is 1, -1, 2, 0, 1, -1, 0, 0, 1. So the rank of A equals 3. So the A is invertible. We use the rank to determine whether the matrix is invertible or not. Let's see another example. If A is -1, 4, 5, 2, 0, 0, 0, -1, and 1, -2, -2, 0, and 0, -1, -1, 0. Is A invertible? Because there's too many zeros here, maybe it's easier to find the determinant. So we use the determinant to find to determine whether A is invertible or not. -1, 4, 5, 2, 0, 0, 0, -1, 1, -2, -2, 0, 0, -1, -1, 0. We expand the determinant, expand the determinant in terms of the third row, the second row. That is -1. This is the A2, 4. So that is -1, 2 plus 4. And that is -1, 4, 5. 1, -2, -2, 0, -1, -1. That is -1, 4, 5, 1, -2, -2, 0, -1, -1. And then we use the third column minus the second column. The third column minus the second column equals the -1, 1, 0. 4, -2, -1. That is 1, 0, 0. So expand. Oh, that's negative. Expand this this determinant by the third column. It's -1 times 1. That is 1 here times 1. 1 plus 3. And there's 1, -2, and 0, -1 left. So that's -1 times -1. That is 1. Does not equal 0. Because the determinant is non-zero, so A is invertible. That's the inverse matrix.